month, though. Tonight's speaker is John Tobin. Honored to have him here tonight from NRAO. He's been there since 2018, right? Yep. Yeah. 2018. Yeah. I just asked him an hour ago, so I know. Anyway, he's going to talk tonight about the frontiers of solar system formation, and he is a science-ready data products project scientist at NRAO, and his research includes star and planet formation, young protostars, protostellar, protoplanetary disk formation, and so he's got this great presentation for us tonight. And whenever you're ready, John, thanks so much for coming.
Okay. Well, thank you very much for everyone and for the opportunity to speak. So I'm John Tobin. I'm a scientist at NRAO, and we are just down the road. So you may have passed us on Edgemont Road coming up. And so I've been there. Well, this is my second stint there. So this current stint, I've been there since 2018, but I was also here 2011 to 2014 when I was a postdoc. So I love Charlottesville, and that's why I'm back. But yeah, I'll be telling you about frontiers of solar system formation. So I'll have, there'll be lots of pictures. I think there'll be something for everybody in this. So there'll be images from ALMA, VLA, JWST. So if you don't know what VLA and ALMA are, that's okay, I'll show you. But JWST, I'm sure most everyone has heard of, since that's frequently in the news. Yeah. Okay, so I'll just first tell you about a couple of new things NRAO is working on. So one of them is the next generation VLA. So the Very Large Array, the VLA, has been out in New Mexico and commissioned in the 1980s. You see the classic VLA dishes here, but they're working on a next generation telescope to replace the original VLA. And a major milestone was completed just last month, where a prototype antenna was constructed, and construction of it was completed, and they handed it over to NRAO for installing receivers and then putting it through its paces to see if it meets the specs for the kind of dish that they need. And so this is not a rendering. This is a real picture of the dish out in New Mexico right now. And there's a webcam, so you can see it. I don't think it's doing all that much, but it was kind of cool to see the construction proceed over the course of several months, where they assembled the thing on the ground, and then on February 7th, they had a big lift of the thing to put it up on the pedestal. And so the design is a bit different from the standard VLA dishes. It has like an offset feed, so sort of a little bit like the mini satellite dishes that you might see on people's houses, or if you know what the Green Bank telescope looks like, it's similar to that. But I think that the Green Bank has the feed up on the top. This one has the feed on the bottom, just because it's easier to get at to fix.
What's the size of it?
Oh yeah, it's 18 meters. So it's okay. A bit smaller than, like, these dishes in the background. Those are 25 meters, so it's a bit smaller. So you get a bigger field of view with the dish. But the key power of the next generation VLA is that they want to be 10 times the sensitivity, 10 times the resolution. So to get 10 times the sensitivity, you need a lot of these dishes. And so the overall plan has 244 dishes spread across the US. So this is what it's meant to. So all of these red dishes, this is sort of really a bird's eye view of the entire, not the entire array, but the entire array that the entire main NG-VLA array. And so it's still centered on the VLA site, but there's antennas that extend into Arizona, into Mexico, and into Texas. And so that's the notional plan. And then if you zoom in on the central region, there's going to be, kind of on the footprint of the current VLA, they're going to have a spiral configuration of the dishes. And so that gives you, and so with the interferometer, that gives you a very nice image synthesis. So because you sort of we're approximating like what a filled aperture telescope would be with all these small dishes. And so when you arrange them in a spiral, you can make very nice images. And then zooming into the core here, this is about like this is now like 1.5 kilometers. There's going to be a dense inner core. And so, like, as you can imagine, you spread the dishes out to get resolution, but if you want to be able to image large structures, you're going to need a bunch of them packed closer together. And so this is meant to give the telescope the power to both like image large things that might be faint, so things like nearby galaxies and things like that. But then you need high resolution to resolve things like the central black holes of quasars, or to look at things that I look at like protoplanetary disks. You need the exquisite resolution. Yeah.
So that section kind of random.
Oh, yeah. So the randomness is actually meant that the randomness actually helps in this case, because when it gets a little bit technical, but when you're trying to use an interferometer like this, a bunch of dishes to link together to act as one larger telescope, you want it to, you can think of this as sort of sampling a really big mirror. And so when you want to really randomly sample that big mirror to get the best possible image quality. Because if you can imagine, if you just had these like sort of on straight tracks, that actually leads to a very complicated, it leads to, yeah, exactly. It puts artifacts in there that then you have to back out through a process called deconvolution. Yeah. And so, and so that's an even shorter, that's a bunch of 6-meter dishes meant to image even larger scale structures. Yeah. Yep, just like ALMA. Yeah, if you're familiar with ALMA, yeah, it's meant to. That's sort of they're sort of using ALMA somewhat as a basis for how they're arranging things, but again, it's going to be different because it has to be much. It's like kind of like ALMA, but on a bigger scale and lower frequencies. Because this is meant to do like down to 1 gigahertz all the way up to 116 gigahertz, and so that's at wavelengths that's about 1 meter to about 3 millimeters. And then, but zooming out once more, now these are the very long baseline stations. So these are the blue dots, and so you even have a couple out in Hawaii, then one in Puerto Rico, and then Virgin Islands. And so this is not only replacing the VLA, it also replaces the very long baseline array. Yeah.
Funding already been allocated.
No, no, funding is not allocated. Oh, sorry. Yeah, the question was if the funding had already been allocated, and no, the funding is not allocated. That reminds me of a quick plug I wanted to make. So at NRAO, we are a facility operated by the National Science Foundation. So if anyone has been following like the fiscal year 2026 budget request, science gets cut massively. So if you're interested in contacting your representatives to tell them that they should continue to fund science to keep the U.S. competitive in science, everyone that works at NRAO and here in New Mexico and down in Chile would very much appreciate that, because that's what keeps us running. I think it's probably almost all of our operating budget comes from National Science Foundation.
Wow.
We get a little bit from like outside partners, but that's sort of like pocket change compared to what National Science Foundation provides to us. And it's not only NSF, it's also NASA has also been, NASA Science has been requested to have a steep cut as well. So that's my last plug.
Ray, the trouble with religious trouble with the island out in the Pacific. The mountain they want to put on.
Well, yeah. So yeah, Mauna Kea. So one of the VLBA dishes right now is on Mauna Kea. It is not on the peak of Mauna Kea though. It is like down. Like Mauna Kea has the top of the cinder cone. This is like down on the plateau is where the VLBA dish is. But they want to move. They don't like this would not be on Mauna Kea anymore. The new dish. They've been looking at other sites, and so yeah. So this would well, it doesn't solve all of the problems. So there's a bunch of other domes up on Mauna Kea, but the VLBA dish or the NG-VLA dishes would not be on the top of those mountains.
Got a station in Puerto Rico. Is that where Arecibo?
Yeah, that's where Arecibo was. So there'd be a station there, and then station on the Virgin Islands, which one of the U.S. Virgin Islands, which there is currently a VLBA station there already.
So assuming you get funding, this will salvage some of the facilities at Arecibo.
Yeah, I think that it could reuse some of the facilities at Arecibo. Yeah. All right, so now getting into the science portion, I think I'm going to focus mostly on things we don't see in the visual spectrum, but I'm going to try and give you a comparison. Like, this is how we see it in visual, but this is how you see it at other wavelengths, to just demonstrate the power of multi-wavelengths for astronomy. And then I'll give you an overview of like how we study single and binary star formation using the infrared from ALMA and the VLA. And then I'll show you some new results from the studies of star formation. So with JWST toward the Orion molecular cloud. And so you get some really detailed views of star formation and feedback. And then I'll talk about a special kind of water and water ice. We'll see if I have time for that. But I mean, just put everyone on the same footing. This is like the electromagnetic spectrum, and what we see with our eyes is just this really tiny portion of it in visible light that we see from like violet all the way out to red. But there's a whole lot of other parts of the spectrum, going from gamma rays, X-rays, ultraviolet, and then infrared, which probably a lot of us are familiar with, just because we feel this heat, and then microwaves and radio. But if we think about a typical galaxy, this is what the spectrum looks like. So I've kind of aligned this more or less to line up with the spectrum, but visible light is right around here. And so you might get a bunch of emission lines, and then you have continuous emission from the stars in that galaxy. But then if there's a star-forming galaxy, this one's called ARP 220. It's a very famous star-forming galaxy that has been studied extensively. You actually have a big bump in emission. It's actually brighter and more luminous out in the far infrared. So this is about 100 microns. So that's well beyond what your eye can see. But without infrared telescopes, you wouldn't know that any of that light is there. And what that is it's warm. This is like cold dust that's going to be forming stars. And then if you go a little bit further out into the radio, so now this is like cold dust emission, and then it's falling off like a black body spectrum once you're looking at wavelengths a lot longer than the peak of that temperature of that black body, then it falls with a steep power law. But then once you get out to radio wavelengths, your spectrum starts going back up again. And that's because you have two different types of emission, not just black body radiation, but you have what's called synchrotron emission. This is relativistic electrons spiraling around on magnetic field lines. Usually you see those in like the outflows coming from the AGN of galaxies. But then you also have what's called free emission, which is electrons that are interacting with protons. They have a near miss with the proton. They divert their direction, and they emit a little bit of radio light, and that's called free emission or Bremsstrahlung radiation, which that's German for breaking. All right, and so I'll probably spend most of the talk out here in the infrared. Okay, so this is the galaxy M51. Oh, I didn't notice this was here. Maybe I can get rid of it. Okay, there we go. And hopefully they can still see me online. Okay, so this is the galaxy M51 that you see in visual light. This is one of the iconic Hubble images. And so you have a beautiful grand design spiral galaxy, and then right here, and then you have a companion elliptical galaxy up here. And now if you look at, so this is what you see with visible light. But if you look at radio wavelengths and look at a specific atom, if you look at the hydrogen atom, for instance, this is what the galaxy looks like. So now I'll just blink back. So you see the core of the galaxy is very bright, so in the center of the galaxy. But if you look at this with something like the VLA at the hydrogen 21 centimeter line, a lot of the things that were dark in here, they start to glow in the radiation of atomic hydrogen. So this is sort of like a line, astrometry by PowerPoint, so it's not exactly a line, but it's pretty close. And then the X up here is supposed to mark the location of that companion. So there's a lot, and then if you zoom out, if you back out of this even further, you can see there's a bunch of atomic hydrogen even further out from this galaxy. And there's the stars, and there's not a lot of stars associated with that either. So when you look at one of these galaxies, we're looking at what the stars, looking at how the stars are shining, but there's a lot of other stuff that you can see that is in those dark regions that they look like they're devoid of emission, but really they are, they're going to be the fuel for further star formation, but they're just not, the stars haven't had time to turn on yet. Now, if we come back to that optical image and we zoom in toward the center of it, so now we're looking toward very much in the center of that galaxy, and we're going to look at a different kind of emission. So instead of atomic hydrogen, we're now going to look at the molecule carbon monoxide. And so you may think it's weird. Okay, you're looking at carbon monoxide in space, but the carbon monoxide, it traces those dark lanes very well. So I'll blink back and forth a couple times. That's because those dark regions, that's dense, dusty material that, again, it's going to be forming, this is going to be the fuel for star formation within this galaxy. And so atomic hydrogen is the most common element in the universe, and molecular hydrogen is the most common molecule in the universe. So you may be thinking, okay, why aren't we just looking at molecular hydrogen? But molecular hydrogen, its properties are such that it doesn't emit very strongly in the cold gas that's going to be doing the star formation. And so we have to use other molecules that we call tracer molecules, like carbon monoxide, to tell us where that molecular hydrogen is and how much molecular hydrogen is there. So we're using, so carbon monoxide is like the best tracer we have of molecular hydrogen in extragalactic systems, as well as in our own galaxy. So it's a very useful molecule. Yeah.
Hey, John, what is the ratio of carbon monoxide to hydrogen?
Oh, yeah. Carbon monoxide is about 10 to the minus 5 or 10 to the minus 4. So like for every 10,000 molecular hydrogen, there's going to be one carbon monoxide. Okay. And that's in the local universe. Yeah. That actually changes with redshift because you need higher metallicity. So you need to have had multiple generations of stars to enrich the carbon and oxygen in the universe. And so as you look further back in time, you get less and less CO tracing the molecular gas. All right, and so now if we look at one of these little blips on here, this is something that maybe is analogous to a star forming region in our own galaxy like Orion. And so now we're closer to home. And so this is the Orion that we all know and love from the winter sky. So Orion is basically done at this point. It's, yeah, we'll see it again in the fall. So Orion is one of the most iconic constellations for multiple reasons. So if you're able to see with an H alpha filter, you can see the nice Barnard's loop here. I don't know if you can actually see it with a photomultiplier and an H alpha filter. Yes. Okay. Great. Oh, okay. And lambda Ori up there. Okay. Great. Yeah. Oops. Yeah. Yeah, but it used to be like you would never be able to see the Barnard's loop with the naked eye, but you can see the Orion Nebula here, and the Orion Nebula here is really a star forming factory. And I think there was something out there that said Orion star forming factory. So if we now, I'll just take away the visible light image and just show you the main stars of the constellation. There's a lot going on that we don't see in an optical light image. So now, first I'll show you, this is the atomic hydrogen. So this is like the cold atomic gas from our galaxy. This is from the NRAO 43 meter or 140 foot that's out in Green Bank. So this is an older image of it, but it shows you, okay, there's some gas out there. It doesn't really tell you a whole lot. But now if we switch to carbon monoxide, now the carbon monoxide is showing us where that dense gas is. And so if I blink between these, you can see they don't really correlate all that well in this case when we're looking at things close up. But this is telling us where all of the dense gas is. And so here where the Orion Nebula is, there's a bunch of dense gas and it trails downward. Up here at the Horse Head, there's a bunch of dense molecular gas and so forth. And that's where the newborn stars are forming. And so we may think of, like, the main thing you may think of with Orion is the nebula, and that's where the new stars are forming. But really, there's a whole lot of other stuff that we don't really see in Orion that is also actively forming stars. But what we can see with the telescopes, with our own eyes, are really the massive stars that have broken out and are blowing away a lot of this dense molecular gas. Yeah.
So those regions with disjoint here, is that
Are the regions truly disjoint, or is there anything that would block radiation at that wavelength that, you know, that darkness between, let's say, the belt and the sword,
Yeah, this here.
you know, is it real, or is it an artifact of an obscuring layer? And do you get obscuring layers with this sort of radiation?
Oh yeah, at this wavelength, so this is like 3 millimeters wavelength.
Okay.
There's really not any obscuring,
Okay.
anything that's going to obscure it, unless you had like some sort of gigantic brick out there that could
Okay.
totally block the radiation. Yeah, but yeah, this is sort of it's thought that these are two separate clouds that might be on the edge of a supershell from a supernova remnant. That's one of the ideas. I think the literature on these has changed a lot in the recent years because Gaia, because of the Gaia mission from ESA that gives us the astrometry of all the stars. You can figure out the 3D structure of these much better than we were ever able to before. All right, and so that's the carbon monoxide, and then now I'm going to show you the warm dust. So the warm dusty emissions. So this is particulate material that's out in the interstellar medium. It's probably the most analogous thing on Earth is like soot that comes in from things burning, like the wild. If you remember, I think it was 2 summers ago, we were getting the wildfire smoke here. That's basically what this stuff is. It's like really like fine micron-sized particles out in the interstellar medium. And so this is being heated up by stars. And so the regions where the star formation is most active glows the most brightly in this dust emission. And so the Orion Nebula, you get a lot of bright emission, and then you get a bunch up here near the Horsehead Nebula. Then you see there's some other pockets of star formation out here and over here. This over here is the Rosette, actually, the Rosette Nebula. And then if you go to now ionized gas, this is going to give you yet another different view. So now this is ionized gas at 1 gigahertz. And so you see the Orion Nebula shows up quite nicely. You get Barnard's loop here, you get Lambda Ori, and then you get the Rosette up here.
like a proper pointer?
Sure. Yeah, the batteries are fading fast in this lens. Thanks. Okay, so with Orion, there's a lot that we see. There's a lot that we can see just behind this constellation, or it's not even really behind it. It's part of the constellation that we don't see with our own eyes. And if we zoom in a little bit more, just on the nebula itself and the areas of where stars are forming most actively. Now this is a color composite image of the optical light, which it may not actually be optical. I might be mistaken on that, but it's sort of a ghostly view of it. But then this is dense molecular gas. So this is now a different molecule. It's not carbon monoxide anymore, but this is ammonia. And so something that you might think of more as like a household cleaner actually forms very readily out in the interstellar medium and traces really dense gas that's going to form stars. And so it forms what we typically call like an integral shaped filament in Orion.
Yeah.
But this filament is really the backbone of star formation in Orion. And so just to show you another one of these, before I get to that, then now if we zoom back in and switch to the optical, this is what HST shows us of this region. So this is now the optical image with HST. So the trapezium is right here. So which if you have good seeing, you can actually resolve those with even a really nice small telescope. But the thing that I've always thought is really cool about these Hubble images, and one of the things that got me interested in star formation in the first place, is that Hubble looking at the Orion Nebula gave us some of our first views of the disks around forming stars. So if we now zoom way in near the bright stars, these are images of individual protoplanetary disks that are around young, like kind of low mass stars, things that are probably even less massive than our sun, more wimpy than our sun. And so, but since the protoplanetary disks are cold, they're not really emitting strongly at optical wavelengths. They're sort of like that really cold material seen in the far infrared and radio wavelengths. But because they are in front of the bright Orion nebula, you see them casting a shadow on the nebula and you see them superimposed. So all these little black smudges, that is the dense gas and dust that is actively forming a new solar system around its host star.
Oh,
The host star is embedded in.
Yeah, so like, for instance, this guy right here is a little star there. Yeah, it's a little star there that you don't, like, they're obscured heavily by like their own disk, but it's casting that shadow on the nebula, and so it creates that. Yeah.
That's kind of a bright spot. Is that going to be this emissions coming from the star, and then some of them have more of a red spot? The third one down. I'm sorry. Over on the left-hand side of the third one down.
Third one down.
Yeah, either that one or next. That's right.
Okay.
So like those
Yep.
two, you have red dot and the bright dot.
Yeah.
John, you'll have to repeat that.
Okay. Yeah. So the question was about like why you see some of these have white dots and some of them have red dots on the where the stars are. And so that's a good question. So there's a bunch of things going on here. And so one of them is that some of these stars they're viewed at different orientations. So if you imagine a protoplanetary disk is like a pancake, like if you look at it, like if you're looking at pancake edge on and the stars embedded in a pancake, imagine a blueberry, you're not going to see the blueberry, but if you turn it over and look at the flat side of it, you'll be able to see that blueberry. And so it's sort of a similar thing where depending on your orientation, you might see more or less of the star. And so the more you're looking at it edge on, that star is going to be obscured more. And so you're going to block out all the blue light, the green light. And so you're left with the red light coming from the star. But
Are the bright dots, so bright red dots, like in that one down in the alpha column, is that a star or is that something else?
yeah, that one's going to be a star. And
then the other thing, that's just, I'm sorry, in the same one.
Oh yeah, and this one, I think that is probably so the other thing that's going on is that all the gas that surrounds these stars, these are very close to the most massive star in Orion, one of the O stars that's putting out a bunch of ionizing radiation. And so the other thing that's happening is that it's lighting up the gas around these and ablating it away. And so that's why some of these have kind of funny looking structures, because it's really that intense radiation from that massive star is blowing away the material that surrounds that star. And so that's why you get some of these things that they have like they call it, like, they kind of look like tadpoles. Like you have a bright spot that's facing the O star, and then there's the tail of the stuff that's being stripped away from that star.
So John, how long ago was this identified that you could identify what these things are and that they are protoplanetary disks? How long ago did that occur?
With these, so protoplanetary disks, they've been theorized for a really long time, but to directly see them like this is with Hubble right after they did the optics correction in the 90s. When they looked at Orion, they were able to see this with Hubble. That was the first time that you're able to like get a direct, clear view of one of these protoplanetary disks. But we indirectly knew they were there by looking at because we could see similar stars in infrared radiation, and then you could make models of them and figure out, oh, have all this infrared radiation there, we need a bunch of dust surrounding it, and it's probably a disk. So they were all inferred, but these were the clearest images that we're able to get of these initially.
What's the scale of, what's the scale of those shadows in terms of, let's say, our solar system?
Oh, yeah, these are about the size of our solar system approximately. Okay. So maybe like 100 astronomical units across, okay. So roughly a bit okay. Larger than the orbit of Pluto. Good question. Yeah, so these are obviously very iconic images from the early days of Hubble. And I think these are probably not the first ones Hubble did. These are probably ones when they revisited it with even further upgraded instrumentation. Okay, so now we're back at the big picture of Orion. And now if we sort of go to one of these backwaters of Orion, so away from the main nebula where you have the highest concentration of stars, but all of this gas down here is also forming stars. And so this is another dark filament where if you look at an optical light, it sort of looks again like a hole in the sky, and you have all of that background light, that visible light is blotted out by the dense dusty material. But if you look at that in the submillimeter, so this is now submillimeter radiation. This is radiation that has a wavelength of about 1 millimeter. Now all these things are glowing because you're seeing the emission from the cold dust, from the cold dusty material. And then these bright spots in this filament, these are going to be your sites of star formation. And so now I'll show you like a cartoon view of what those look like. And so like this is sort of the diagram of what a protostar looks like. So it's surrounded by an envelope of material. So this envelope, this kind of spherical looking thing, this is like what one of these little dots on here. That is about the size of an envelope around a protostar. So about 1/10 of a parsec in diameter. So this is much larger than our solar system. And then this envelope, to be forming a protostar, this material needs to be gravitationally bound and it's collapsing. And because this material, as it collapses, has a little bit of angular momentum, and that's going to cause the rotation of it to increase as it falls inward. So similar to like how you have a figure skater, when you sort of spin with your arms wide and then you pull your arms in, you spin a lot faster. Don't try that on ice skates unless you're a skilled skater, because you'll probably fall. But that causes the formation of that protoplanetary disk that we saw in those other images. And then the interaction of that protostar that has formed in the center and the magnetic fields of the star and disk, that's going to then launch an outflow of material coming out from this protoplanetary disk. And so I think I didn't point it out in the other images, but there might have been some little outflows and jets of material coming out of them as well. But I have a couple other images I can show later.
Hey, John.
Yeah.
Quick question. So for the sun, one solar mass, what is the distance before a hydrogen atom is captured, orbitally captured? Any ballpark idea what that,
Oh, to capture a hydrogen atom, at what distance?
Yeah, how far out in the solar system or beyond the solar system are those hydrogen atoms captured by the sun?
Oh, that can be complex, but it depends atoms are more difficult, but if it's like a rock, it depends on how fast it's moving. If it's like I mean, if it's moving, if it's out like say at several hundred AU and it's moving a kilometer per second, it may not be captured. It may already have escape velocity, but really it just depends on what is your escape velocity out at that
Gotcha.
out at that radius. Yeah.
Work clouds, cache.
Yeah. Yeah. So yeah, or yeah, the Oort cloud. Yeah, there's a lot of debate about that. Some can be captured, some may not be. Yeah, but what I said, the atoms are more difficult. It's because you have the solar wind that's also pushing stuff out as well, and that can make it more complicated about whether like an atom could be captured or not. All right, and if you want a more detailed view of like all the different physics that are going on, this is like another more detailed view. But you sort of have the jets from protostars that are shooting out. They create these little shock knots that can actually be seen moving away from the protostar. And then here, this is like the star forming cloud, and you have the infalling envelope around that protostar. Then you can also get these other things that are like the formation of stars isn't from a sphere. It's can be from very irregular objects where you approximate things in spheres, because it just makes all of the math a whole lot easier. But you can get these things that we call streamers, which are I think they're exactly how they sound. They look like little thin ribbons of gas that are falling in through the envelope and feeding the disk with material that material has to then feed through the disk to get to the star. And you're seeing these little columns, we call them accretion columns. This is like the material from the disk flowing along field lines and then landing onto the star. Okay, and so now these aren't real pictures of disks, but these are simulations of what some disks might look like around protostars. And so some of them some of them only have one star, and then you just have a more or less smooth disk, maybe with a little bit of spiral structure that's surrounding that star and feeding it with material. But other ones form with much more massive disks. And if you have a disk that has enough mass in it, you can actually have that disk fragment and form a second star, or possibly form giant planets due to a process known as gravitational instability. But the youngest disks around protostars have really been tough to observe and capture images of, because they're buried within all of that dense, dusty material. And even facilities like the VLA and ALMA can sometimes have trouble seeing them, and you have to really look with some of the highest resolution that are available with those facilities. So now this is now we're going out of Orion, but we'll come back to it, I promise. This is another star forming cloud, and this is what you see in visual light. And so you can see the dark patches of sky here. And then you sort of see some diffuse scattered lights from dust grains in the interstellar medium, and a couple of stars. This is a young star up here as well, and it's sort of illuminating the edge of that cloud. Then if we go to infrared light, this is what we see. And so in the infrared, you're seeing these are the outflows coming from the protostar. That's sort of all this kind of fluffy greenish emission. And the young stars are here, here, here. There's one here you can't even really see a hint of, one down here and another one down there. Now I've lost my train of thought. But yeah, you had no hint of that from the optical image. Like maybe this little red spot here, yeah, there was really no hint of what was going on inside of this cloud without the infrared wavelengths. And so this is from the Spitzer Space Telescope. This was probably taken almost like nearly 20 years ago now, like back in 2005. So, and this was some of the first data that I worked on when I was an undergraduate student working at University of Illinois. And so this was a lot of fun to get into. But the thing that is maybe not clear here is that the resolution on this image isn't all that good. This is about 1 arcsecond pixels on this image, and Hubble has about a factor of 10 higher resolution, and James Webb has about a factor of 10 higher resolution as well. So we get a view of what's happening around that forming star, but we don't get a view of what's happening inside of it. And if we look with a single dish submillimeter telescope, so a 15-meter telescope on Mauna Kea called the James Clerk Maxwell telescope. So this is going to about a wavelength of 1 millimeter. Now we see the cold dust around these protostars. So I'll blink back. And so, yeah, towards those young stars, we see the dense dusty material. And this is the envelopes that are going to be collapsing around those protostars. And so that resolution was even lowered in Spitzer, which is why I kind of look blobby. And so you really don't quite get a view of exactly what's happening with just Spitzer and just with the single dish submillimeter telescopes. And that's why we needed to go to higher resolution telescopes. And so I'll jump back to that in a second. But really, I think what you've probably taken home already is that the keys to looking at forming stars are that you need the long wavelengths to see through all that dense obscuring dust, because that cold star forming gas and dust glows at those longer wavelengths. And then you really need higher resolution. So like typically we get ground-based like 1 arc second on a good night. That's not quite good enough to be able to see these forming disks. And you really need like a 1/10 of an arc second or better. And that's why Hubble was the first one able to see those forming protoplanetary disks, because people have been looking at Orion since since telescopes were around, and the resolution just wasn't good enough from the ground to be able to see those structures. And for radio telescopes, you need the interferometry to get that high resolution. The single dish radio telescopes just don't cut it. And then I've talked mostly about continuum radiation thus far, but there also is the line radiation I was showing you in those earlier slides. And that really helps to see what's going on, because you can use the Doppler effect to see the motion of the gas around stars and around galaxies. So this is an image of what ALMA looks like. So this is in the Atacama Desert. So ALMA, which I've been using that word, but without telling you what it stands for, but it's her Atacama Large Millimeter submillimeter array. And so that's in northern Chile at an altitude of about 16,500 feet. And so it's very remote and there's very little oxygen up there. So all of the workers up there carry supplemental oxygen with them, because it's hard to have enough air to breathe up there. And then the VLA, this one's closer to home. This is in New Mexico. So I mentioned the resolution. ALMA can get a resolution about 5 AU, 5 astronomical units. So about the distance from Jupiter to the sun. So that's pretty good. And the VLA at its highest frequencies can get about 15 AU resolution. And so this is a view of the VLA on a pretty stormy day. So this is not a day where you'd really want to be trying to do the highest resolution observations, because contrary to like popular belief, you do need good weather to get really good images into radio. Like if you're looking at 1 gigahertz, so 1 meter wavelength, the weather doesn't matter so much. But if you want to look at like 1 centimeter, you need really good weather. You need a very stable atmosphere to get those sharp images. Well, if you take the continental baselines, it'll be like milliarc second, like about 1 milliarc second.
The array anyways.
Yeah, this is what the dish is all close together. Yeah, so this is low resolution anyhow, in this configuration. But from the more intermediate baselines, the ones that are like mostly New Mexico, Arizona, Mexico, and Texas, those will get you about like 10 milliarc seconds, which is still really, really good. And so in the nearest star forming region, that is about it's about 1.4 astronomical units. So you can actually start to see the formation of terrestrial planets, or you can see the little clumps that may turn into planets. Yeah, and so now back to our infrared image. And now this is the view that you get and so these are all the protostars. I pointed them out individually earlier, but now if you look at them with the VLA, this is what you see. So now you can actually see that there is something there. It looked like there was nothing, but there is indeed 2 stars forming there. Now this one has 3 stars forming here. And so the scale bar on here is here, so about half an arc second. The image resolution was about 10th of arc second.
That's all.
Yeah. Yeah, this one had 2 stars, and this one also had 2 stars. And so these ones are,
It's like binary stars.
yeah, exactly. Yeah, so these are actively forming multiple stars right now. And then we do have images of like the singletons, like this one and this one, but they're less interesting to look at. They're kind of like one of these dots. But still, we see that there's multiple stars there, but we don't quite see what's going on around it. So if we now zoom in on this guy here, so now you can see with the VLA image, it looks like there's some stuff around it, but we don't get a very good view of it because the sensitivity just isn't good enough. But now if we use ALMA, which is a shorter wavelength, and at shorter wavelengths, all of that dust emission is brighter, this is the view that we get. So now, what was really interesting about this system is that this is the brightest thing. And you might think, okay, that's the brightest thing. Maybe that's where the most mass is. But when you look at this disk, and it looks blurry when you're up here, but back there it looks it's much more clear. But this whole thing is organized around this as the center. And so the most massive thing is actually probably here at the center. And then this thing is just so bright because it's in the process of still forming and has a bunch of cold gas and dust around it. And we've looked at this in the carbon monoxide molecule, actually an isotopolog of carbon monoxide, which is getting into even more detail. But we can see that the rotation is centered right here. There's no discernible rotation around this thing. So we've confirmed that all of the mass is kind of right here at the center. And so there's at least 3 stars forming here, possibly a 4th in the center, which may be the dominant gravitational mass.
Here in the middle are probably more massive than that one right.
Yeah, though here in this little dark spot, when we looked at this, we took a yet higher resolution image of this. It's a little ugly to show on the projector. It's like kind of like we sort of try to live at like the limit of sensitivity. So once you're at the limit of sensitivity, things aren't quite as beautiful, but there's another little lump there that might actually be a massive star kind of at the center of this, about a 1 solar mass star. So it's either these things have a bunch of mass or something there that we're not seeing has most of the mass. Yeah, and so, yeah, we're starting to run low on time, so I'll try and wrap up in a few. All right, and so, yeah, so ALMA gives us this beautiful view of the forming disks around protostars. And so we think this is one of those ones that may be forming multiple stars due to gravitational instability. And so when we first got this image, we were floored by how amazing it was, because I mean, it looks just like it looks a lot like the simulations, but we're actually seeing it for real. And we've looked at a whole lot of these in Orion. So this is the view of the Orion molecular cloud. The trapezium and the Orion nebula are right there. So we're looking at the extended Orion molecular cloud, and we looked at all of these points, these little points on here. And this is the view from ALMA, and then this is the view from the VLA. And so you see a plethora of different systems. You see things that look kind of disky and things that have multiple stars that are.
VLA, they're on the same scale.
Yeah, they're on the same scale. Yeah, so. Yeah, definitely. Yeah, and that's because of that cold. That's because like the dust shows up a lot better for ALMA, but we kind of see with VLA, the dust is there, but we're kind of only seeing the tip of the iceberg due to the sensitivity of since it's less sensitivity. If you had an NG VLA, you could see basically the same thing probably. All right, and so now I'm going to cap this off with the James Webb. So now again, we're back to Orion. This is the visible light image. This was from an amateur. This was actually taken about 10 years ago, and I think I've happened to find this one on like NBC.com. So this is from that a guy took in his backyard in North Carolina. And then if we look at this now with the infrared with Spitzer, this is the view that we see. So now you see up here, which was basically black between like the Running Man Nebula and the Orion Nebula, it looks like there's nothing going on in the optical. There's not a whole lot going on there. But when you look in the infrared, there's actually a ton going on there. And you see this dark filament, which is actually one of those star-forming filaments that just appears dark in the infrared because it's blocking out the bright background radiation. So now if I zoom in to this region here, this is what you see with Spitzer. So trapezium is down here, and then you got all of these like kind of fuzzy things showing up. These are the young newborn stars that they don't show up too well if we zoom in, but they don't, like, it's kind of fuzzy. It's because of the resolution of Spitzer. So Spitzer had a mirror of this size compared to James Webb of 6.5 meters. So James Webb is almost about a factor of 10 higher resolution just by mirror diameter alone. And so now, you probably know what I'm getting at. So now this is the view of Spitzer. And now this is the view of James Webb. Oh, shoot. You know what? This didn't actually, it didn't line up. Oh, I did that, but that's unfortunate. But yeah, this is the view of James that we get with James Webb towards this upper region here. And now this is James Webb viewed on a projector from back here. This image is actually huge. So now I can, it's a little jumpy, but, and still this barely does it justice because you can still zoom in yet further on this image. And so you can see the jets of gas coming out of protostars. There's a really big one coming across here. Then this is a really active region of star formation happening down here, where there's an intermediate mass star forming right there. Oh, they are a couple 100 kilometers per second. Okay, I have to look at this. Won't let me advance. I was going to go to it. I have a still of one of the regions on the next page. Yeah, and then it'll go to the next one. Okay, yeah. So now I just give you a still of it, an even better zoom in of it. And so yeah, there's a protostar here driving this beautiful jet of material. And so what you're seeing, all this kind of like fluffy material, this is molecular hydrogen that's been, so the outflow from the protostars is running into the ambient material and creating a shock, which heats up and excites the gas and makes it glow. And so on this one, you can kind of see two structures. You see a bigger structure here. This is like that bow shock that was on, I think this slide, a bow shock here. Oh, and my crop didn't work up there. Shoot. But you can see like a narrow jet coming out here and then a wider angle outflow coming here. And then the protostar is sort of like right there. It's kind of at the tip where it's still just a little bit buried, even for James Webb. And this is false color, like 2 micron, 3 micron, and like 5 micron image. And so these are brand new data. Oh no, this is coming from the protostar. So these are kind of out of the influence of the Orion Nebula itself. So they're not being impinged on by the massive hot ionizing O stars, but these are being driven by the protostars themselves. But there's not a lot of they're not powerful enough to do photoionization themselves. So a lot of this is still molecular gas, but there's a bit of atomic emission that's like at the center of these jets where the material is moving the fastest and creating the most powerful shocks to break apart molecules. Yeah, and so that is probably a good place to end it with there. Yeah.
About the jumbos, no doubt. Jupiter
Yes.
mass. The question is going to be about the Jupiter mass binary objects. Are they being observed on these kind of images, or are they even more magnification?
They could be observed in these images, but those were seen in another part. They were seen further south towards the main nebula of Orion. but I mean, we haven't, like, these data we got in March of this year. And so this is all still very fresh, and we haven't really dug into it a whole lot. So, I mean, there probably are a bunch of interesting things we haven't even looked at yet. So, I mean, one of the things we got to do is find all of the stars in the image and see what's going on with them. Because there are indeed protostars that we did not know of before getting to James Webb images. So there are new things there. We didn't know everything from Spitzer, but so there is new stuff to see. In addition to all of the greater detail that's revealed.
Good questions. Any other questions? Oh, come on. We usually have like 50.
Yes, I was
Going? All right.
yeah, I was just going to jump to the summary slide, but
Oh, okay, we got one
yeah.
here. Oh, that's a general question, no?
No.
Oh, okay, okay.
Well, then, without further ado, we want to thank our speaker. We know we have a tradition here at the Charlottesville Astronomical Society. All of our speakers and only our speakers ever get the coveted cast coffee mug, keep you going at night when you're observing. We draw your attention to this fancy feature in the back here. We have all the major meteor showers.
Oh, nice.
So that way you know when not to step
Yeah.
outside, because. Oh.
Yeah.
Or in the case of radio
Yeah.
astronomy, there'd be a lot of radio interference,
Yeah.
all that plasma.
Yeah. Yeah, thank you.
I do have one more question for you. So
Yeah.
This is James Webb you have now. So what is the expectation for the next gen of, not just the VLA stuff, but the next gen, what are you hoping to see on the next generation of telescopes and the like?
Oh, what am I hoping to see, or the next gen, like something beyond James Webb?
Yeah, beyond James Webb, yeah.
Okay, well, I think right now we don't quite know enough, because I think a lot of the James Webb data are still really fresh. But I mean, one of the things that we're sort of blind to right now is the far infrared. There's like the only place you can really observe the far infrared. So this is like 10 micro, or about like say 30 microns to about 350 microns. It's a region of the spectrum that you can't observe from Earth because the atmosphere completely blocks it out. Like atmospheric water vapor just obliterates it. So that's I think getting high resolution in the far infrared would be one of the next great things, because we've had Herschel and Spitzer, which allowed us to observe at those wavelengths, but not with high resolution and not with great sensitivity. So you could do much better now at those wavelengths than you could like when those were designed and built like 20, 30 years ago. So that would be fantastic. But
Yeah.
But I think something like being able to see like what is going on inside of this thing. And so like the next generation VLA would really be needed for that, because ALMA may have the resolution, but this is so dense, it's opaque for ALMA's wavelengths. And so you need the longer wavelengths where the dust is more transparent. And then you have the sensitivity to be able to see the gas as it's flowing around down towards the star.
That stuff.
You have one question online from Marshall. Did you work with John Dickel at Illinois?
No, I didn't work with John Dickel. I think he had retired just as I was starting as an undergraduate there. So, but yeah, the name is quite familiar. And when I was at University of Michigan, I think he went to Michigan. His thesis was on the shelf of all the theses at University of Michigan as well.
Oh.
Question.
Right.
Question from Carl.
It's on.
It's on. Just what is the really large scopes that they're building down now? And I think in Chile that it's a 30 millimeter. What's that going to add to what 30 meter, not millimeter, 30 meter scopes? Yeah, thank you. What will that add that we can't already see with what we've got? I mean, what's that going to do for us?
Oh, so are you referring to like the CCAT telescope, or because there's a couple of different ones. There's like well, Well, 30 meter, I'm sorry, ELT, yeah. That's what you're getting at. So, I mean, the ELT, so that operates, so the key thing that you get there is that it gives really high resolution, and it can operate at both optical and near and mid-infrared wavelengths. So you can study, so the thing you get from the ground that you don't really get into space is, one of the things is spectroscopy, is that on James Webb, we have spectroscopy on James Webb, but the resolution of those spectrometers is actually pretty coarse. You can only see like really fast motions of gas. But with something like the ELT, you can have much higher spectral resolution. And so you break up the light into more component wavelengths. But when you break it up further, then you need more sensitivity to actually detect that light in a reasonable amount of time. So it'll let you be able to see what's happening very close to forming stars. I mean, you'll also be able to see, like, you may be able to see the light that is coming from, like, transit spectroscopy of exoplanets, not just from like hot Jupiters, but you might be able to do like transit spectra of super Earths. Yeah. And then you're really just at the optical wavelengths. You get because you hook them up with adaptive optics, you can get exquisite resolution and be able to directly image like close in exoplanets that you can't do with the current telescopes.
Anybody else? Last chance, going once, twice. All right.
You done?
All right.
Thank you so much, John.